Welcome back to The Deep Dive, the show where we take the absolute fire hose of new knowledge and try to distill it down to the essential insights you need.
And today we are opening a report that I think fundamentally changes the entire conversation around AI. We're really moving past the question of, can these models write decent code or generate a blog post?
Right.
We are asking, can they genuinely invent new science? Can they act as intellectual co-authors on the very frontiers of what we know?
And according to this new GPT-5 scientific acceleration report, the answer is a pretty profound and, more importantly, a documented yes. Our mission in this deep dive is to unpack exactly how this model is accelerating discovery.
And we're talking across fields as diverse as mathematics, theoretical physics, even immunology.
It's this idea of a compression of the scientific timeline. It really shifts what a hard problem even means anymore.
The central finding, like you said, is that transition. GPT-5 is no longer just a productivity tool, something that speeds up a task you already know how to do.
Yeah, it's not just a faster calculator.
Exactly. It's an intellectual contributor. The report lays out these specific cases where the model generated novel proofs. It proposed mechanistic hypotheses that the human researchers, the experts in the field, had actually missed.
And when you say magnitude, we're talking about verifiable results. Things that would have taken human experts months, maybe even years to achieve.
And that's being compressed into minutes or a few hours of collaborative work. I mean, the report documents 4 distinct verifiable new breakthroughs in mathematics alone.
4, just in math.
All achieved with significant AI assistance. This isn't just, an evolution. It feels more like a revolutionary change in how science gets done.
So, okay, let's set the stage. What is the core problem here that AI is supposedly solving for these researchers?
Well, if you look at the challenges a human or researcher faces today, you can really boil down to 3 main roadblocks. And AI seems uniquely positioned to just obliterate them.
Okay, what's the first one?
The first is just sheer information overload. The number of papers being published it's just impossible for any one person to keep up with.
I feel that. And the second has to be the siloed knowledge, right? What the report calls the barriers of language.
Exactly. If you're an expert in, say, convex geometry, you're probably never going to search for papers written by a theoretical computer scientist.
Even if they solved the exact same problem but just used different words, different jargon for it?
Precisely. The concepts are the same, but the vocabulary is a wall. And the third roadblock is simply the immense time costs.
The grunt work.
The grunt work. Laborious verification, running complex calculations, trying out 1,000 different parameters in a simulation, checking every single step of a long, convoluted proof. These are the time sinks that just kill human productivity.
I know that feeling from my own research. I mean, I've definitely seen the shift firsthand. A few years ago, LLM saved me maybe 5% of my time, formatting things, drafting an email.
Yeah.
But now people like the mathematician Timothy Gowers are saying these models can solve really complex, well-defined subproblems in seconds. He calls it the speed gap, and it's just getting wider.
And that speed gap is being powered by what I think is GPT-5's key innovation here. It's this ability to focus on core concepts, not just keywords.
So it's understanding the meaning behind the words.
Yes. It can uncover these forgotten or hard-to-find connections across different fields because it understands the underlying math or the physics, not just the specific vocabulary people used to describe it 20 years ago.
And this is where it gets really, really interesting for me. It's moving beyond just being a superpowered search engine and into actual reasoning.
That's the leap.
The model isn't just, regurgitating its training data.
Yeah.
In several of these documented cases, the model was shown to reason for extended periods. We're talking anywhere from 5 minutes up to 40 minutes.
To produce these incredibly complex proofs and analytic results. And the experts who worked with it, they often describe the results as having miraculous identities or these really elegant arguments.
So different from how a human would have done it.
Fundamentally different. We're seeing these novel intellectual pathways emerge from what is, let's be honest, still basically a black box of deep computation.
Okay, let's get into a concrete example. The report starts with this warm-up experiment led by Sebastian Buback, focused on convex optimization. Can you set that up for us?
I can. And this was a really crucial, deliberately chosen problem in modern optimization. The goal was to improve the step size condition for gradient descent.
Okay, gradient descent is basically the engine behind most machine learning, right? It's how models learn.
It's the engine. So even tiny improvements here have these massive downstream effects. The step size, usually written as eta, determines how big of a jump you can take towards the solution without overshooting it and just flying off into infinity.
Right, you want the Goldilocks step. Not too big, not too small.
Exactly. So in the first version of the human paper, let's call it V1, the proof showed that a step size of 1 over L was good enough for the algorithm to converge. Human experts later worked really hard and found the absolute optimal, most efficient bound was actually 1.75 over L. Let's call that V2.
So the challenge for GPT-5 was, if we only show you the V1 proof for 1 over L, can you discover the better 1.75 over L on your own? The model had no access to that V2 paper.
A perfect test of independent discovery.
Oh, okay.
But in a matter of minutes, it reached a novel bound of 1.5 over L. And crucially, it used a proof structure that was completely different from the human V2 proof. It basically invented its own highly efficient intermediate solution.
Wait, hold on. Let me make sure I understand the significance of that. Moving from good enough at 1 over L to much better at 1.5 over L happened in minutes, on a problem that defines the speed limit for huge chunks of computational science.
Yes. And the expert estimate was that for a human, getting from 1 over L to that 1.5 over L would have taken a few days of very focused, high-level mathematical work.
A few days into a few minutes, that's real-time scientific acceleration.
It is. But you're right, it didn't hit the optimal 1.75, and that's an important point. Is that a limitation?
Yeah, is that where it falls short?
Well, the report says it's more of a snapshot of capability. They noted that OpenAI's internal versions of the model, when they were allowed to reason for a few hours, not just a few minutes.
Ah, so you give it more thinking time.
You give more time to sit and chew on the problem, just like a human would. And those versions were able to derive the optimal 1.75 over L bound from scratch. It just underscores the potential that's unlocked by letting the AI have sustained focus.
Okay, so moving from that abstract optimization theory, let's dig into the theoretical sciences. This is where the math can get just overwhelmingly complex, specifically this search for hidden symmetries in black hole physics.
This is truly foundational stuff in general relativity. The problem was about discovering the non-trivial lie-point symmetries of the wave equation on a rotating or Kerr black hole.
Okay, you just said a lot of words there. We've got to define some of that jargon for the listener. What exactly are lie-point symmetries, and why do physicists care so much about them?
Yeah, good question. So think of a symmetry as just a transformation, a rotation, a shift that leaves an object looking exactly the same.
Like rotating a perfect sphere.
Perfect analogy. In physics, a lie-point symmetry is a transformation that leaves the differential equation itself unchanged. And this matters because if you find a symmetry, you find a really deep underlying structure. It often lets you simplify or even solve the entire equation.
So it's like a secret key to unlocking the problem.
It is. And for the Kerr black hole, these symmetries are key to explaining really weird features, like why its love numbers, a measure of its stiffness, are 0.
And doing this calculation by hand for a curved space-time like a black hole is, well, the report calls it arduous.
That's putting it mildly. It's pages and pages of tensor calculus, a months-long process of just grinding through algebra. So the expert, Alex Obsaska, first gave this really complex curved space equation to GPT-5 cold.
A cold start. And what happened?
An instant failure. The model thought about it for 5 minutes and then confidently declared that there were no continuous symmetries beyond some trivial ones.
So it was just wrong.
Completely wrong. And this is so important. It proves the AI is not some oracle. It needs direction. It needs a good collaborator.
This is where that art of collaboration, what the report calls scaffolding, becomes the main lesson, isn't it? The human expert didn't just give up.
No, he was clever. He gave it a warm-up prompt, a stepping stone. He gave it the flat space limit of the same equation.
So the same physics problem, but without the black hole's gravity messing everything up.
Exactly.
Yeah.
It's mathematically much, much simpler, but it shares the same fundamental symmetry structure. It's like asking the AI to solve the easy version of the puzzle first, to learn the rules before tackling the hard one.
And after it had that conceptual warm-up, what happened?
The transformation was incredible. On the second try, after about 18 minutes of reasoning a much longer chain of thought,
Right.
GPT-5 produced the full, correct, non-trivial curved space symmetry generators. It found the whole complex structure, including the specific cell player algebra that physicists were looking for.
And these results matched known physics.
They perfectly matched results that human researchers had only found very, very recently. It confirmed the AI had implicitly performed this incredibly sophisticated symmetry computation using what it learned from the simple problem to crack the complex one.
So what does this mean for you, the listener? If you're a physicist or an engineer, this shows GPT-5 can act as an AI symmetry engine.
It compresses a task that would have taken months of tedious, painful algebra into just a few days of focused scaffolding and then verification. But the key is, you, the human, have to know how to break the problem down into those simpler related pieces. The interaction is everything.
All right, let's pivot from that to the problem of scientific isolation. This is the deep conceptual literature search. This is where GPT-5 is supposed to bridge those barriers of language between different fields.
Yeah, and this case study was fascinating. It happened in the context of a new mathematical result, a theorem about something called alpha ratio covers for convex sets. The human authors were proving it for an application in statistical density estimation.
Okay, so a very niche, very specialized mathematical statement. They give this statement to GPT-5, and what happens?
The model immediately surfaces this seminal paper by Papadimitriou and Yannakakis from the year 2000. And it wasn't from a math journal, it was from a theoretical computer science conference.
Yep, OCS, right?
And here's the insight. The computer scientists had used an almost identical concept. They called it an epsilon approximate Pareto set, and they were using it in the context of multi-objective optimization.
Wait, multi-objective optimization is a world away from statistical density estimation. Why did the model make that leap when the human authors, the experts, completely missed it?
Because GPT-5 wasn't looking at the words. It was looking at the underlying geometric structure. It understood that the mathematical object was structurally and functionally identical, even though the humans were using different letters, different definitions, and field-specific jargon.
That is a critical feature. It's like the model is acting as an institutional memory for all of science, connecting these disparate ideas that were solved in isolation just because the humans weren't talking to each other.
And they tested that capability even further using the online database of Paul Erdős's unsolved problems.
The legendary mathematician who left behind thousands of conjectures.
The very same. And there's a nice little meta moment here. The report notes that GPT-5 had actually helped code the online index for these problems in the first place.
Huh. So what did it find in the database it helped build?
It located previously published solutions for 10 problems that were still marked as open, which just goes to show how scattered and hard to find this knowledge is, even with the internet. It's the information overload roadblock in action.
I thought the specific example of problem 515, the one on entire functions, was the most compelling. Can you walk through how a normal search engine would fail there, but GPT-5 succeeded?
Sure. It's a highly technical question about whether a certain kind of function has a path to infinity where an integral is finite. If you do a keyword search for Erdős, entire functions, or problem 515, you find nothing useful.
The keywords are too generic or too specific.
Right. But GPT-5 didn't search for the keywords. It analyzed the structural properties implied by the question, the way the integral constrains how fast the function can grow. And that structure linked it to a 1984 paper on a related concept called subharmonic functions.
And that paper had the answer.
It solved the problem implicitly. It laid out the conditions that would make the integral finite, but it never once mentioned Erdős or his specific problem number. The model recognized the logic was identical, even if the words weren't.
That's the vocabulary challenge. It's not searching for the word X, it's searching for the implications of X.
And it does it across languages, too. For another problem, hashtag 1 of 43, the solution was buried in a little side comment in a 1961 paper. But the real meat of the proof, the foundation for that comment, was in a 1959 paper written entirely in German.
And GPT-5.
Not only found this unbelievably obscure chain of references, but also translated and explained the German proof so the human expert could verify it.
So what you're saying is, for a researcher today, the whole game of following long citation chains, trying to translate specialized foreign texts, or guessing the right magic search phrase, that's all becoming obsolete.
It seems so. You just plug in the concept, and the AI connects the dots across decades and languages.
Let's transition now to the applied sciences, where GPT-5 is working in tandem with researchers. This immunology case study is a perfect example of what the report calls co-investigator level contribution.
This section involved a T-cell biology expert, Dr. Dario Unutmaz, and his lab had this really puzzling observation.
Okay.
If they briefly inhibited glucose metabolism in T cells using a drug, 2DG, during their initial activation, weeks later, those T cells would turn into a much more aggressive, pro-inflammatory type called Th17 cells.
And Th17 cells are generally bad news in this context, right? They drive a lot of autoimmune diseases.
Exactly. They're the aggressors. The mystery was that the drug was washed out almost immediately, but the inflammatory effect persisted weeks later. The lab had no idea what the mechanism for this lasting memory was. Their own hypotheses weren't panning out.
So the human experts, deep in their own field, were stumped. They present this counterintuitive data to GPT-5. What did it come up with?
In minutes, it generated two highly plausible, non-obvious hypotheses. The first was based on a secondary effect of the drug. It's known to interfere with something called N-linked glycosylation.
Glycosylation. That's basically the process of adding sugar coatings to proteins, which affects how they work and where they go in the cell.
Correct. GPT-5 hypothesized that this interference messes with the sugar coating of the IL-2 receptor on the T cell surface. And here's the key biological link. IL-2 signaling is known to suppress Th17 differentiation.
Ah, okay. So if you reduce the IL-2 receptor, you're essentially taking the brakes off the Th17 program.
You're disinhibiting it. You're locking in that inflammatory lineage.
Yeah.
It makes perfect biological sense, but it just hadn't occurred to the expert lab.
That's incredible. It connects a known off-target effect of the drug to the strange downstream outcome. What was the second hypothesis?
The second was about epigenetics, the idea that the brief metabolic shock permanently shifted some chromatin modifiers, essentially creating a form of epigenetic memory that locked in the Th17 program.
And the beautiful part is that GPT-5 didn't just speculate. It proposed a really specific, testable prediction based on that first glycosylation hypothesis.
The mannose rescue experiment. Mannose is a sugar that can fix the glycosylation problem without fixing the main glycolysis problem.
Yeah.
So if the hypothesis was right, adding mannose should reverse the effect. Here's the kicker. The lab had already performed that exact experiment weeks before, and the result perfectly matched GPT-5's prediction.
That is the definition of a co-investigator. It didn't just summarize papers, it correctly predicted the outcome of an unpublished high-stakes experiment.
And they immediately applied this to a huge clinical area, CAR-RT cell therapy for cancer. The model analyzed data showing that this same drug, 2D-DG, reduces the brakes on cancer-killing T cells, these checkpoints like PD-1.
Cancer uses those checkpoints to shut the immune system down.
Precisely. So GPT-5 correctly predicted that a brief pulse of 2DG during the manufacturing of CAR-T cells would significantly enhance their ability to kill cancer cells. And this, too, was an internally validated but still unpublished finding.
The implication for biomedical engineering there is just massive. GPT-5 is suggesting concrete, testable tweaks to clinical protocols that could take years to optimize by hand.
It lets you prune all the bad ideas in silico before you run a single expensive, time-consuming wet lab experiment. It shifts the whole process.
Okay, let's move to maybe the most staggering example of time compression in the whole report. The physics modeling of inertial confinement fusion, which gave us that mind-blowing $1,000 times acceleration factor.
Yeah, this project at Lawrence Livermore National Lab, led by Brian Keith Spears, was focused on thermonuclear burn. In ICF, you use giant lasers to crush a tiny fuel capsule to spark fusion.
The goal here wasn't to model the whole messy reality of it, right?
No, they wanted to develop a simplified model to isolate one key thing, the ideal interface profile between the hot burning fuel and the cold fuel next to it. What's the optimal density shape to make the burn wave move as fast as possible?
Setting up a model like that from scratch sounds like a monumental task.
It is. It's complex partial differential equations, and you have to integrate very specific nonlinear physics. But GPT-5 generated the initial model almost instantly. It incorporated 4 individually complex pieces of physics.
First, Spitzer-Herm thermal transport. What is that, and why is it so hard?
It describes how heat moves in extremely hot plasma. It's complex because the conductivity isn't constant. It depends on temperature in a very nonlinear way. It's fundamental fusion physics, but it's a pain to code.
Then you have the Bosch-Hale DT reactivity and Gray radiation loss.
Right, those are specific formulas for the fusion reaction rate and how much energy you lose to X-rays. And finally, the really tricky one, non-local alpha particle heating. The energy from fusion doesn't just get deposited locally, it spreads out.
So GPT-5 synthesized a high-fidelity model with all these complex parts and then set up the numerical solver for it.
It chose a standard but laborious method called the Crank-Nicholson scheme. It integrated all of this physics and all of this methodology in minutes. The heavy lifting was just done.
Okay, but here's the necessary dose of skepticism. The expert in the report noted that GPT-5 was a bad designer and needed a lot of human hand-holding.
This is the Goldilocks problem in a nutshell.
Yeah.
The model was so eager to please, it would produce results that were, and I'm quoting, null, noisy, or invalid, and then confidently claim it had succeeded.
So the simulation would just be garbage, but the AI would say, look, I did it.
Exactly. The human expert had to spend a few hours constantly pushing back, adjusting parameters, critiquing the output, and saying, no, this is wrong, try again. The human couldn't delegate the thinking. They had to be the quality control.
But when it was corrected?
When corrected, it responded with incredible sophistication. It implemented advanced techniques like fast Fourier transforms to speed things up. It improved the resolution. It was a highly capable, if sometimes misguided, assistant.
And what was the final result of this back and forth?
The exploration found an optimal ridge in the design space, a very specific density profile, a shallow slope with moderately negative curvature that maximized the burn front speed to about 100 kilometers per second. This gives fusion researchers a clear design target.
That's the numerical part. But the real science came from the theoretical verification, right?
Yes, this is the amazing part. GPT-5 didn't just run the numbers. It derived the underlying theory. In the final stage, it derived a traveling wave power balance theory that analytically explained why that specific density ridge was optimal.
It explained the physics behind its own numerical result.
It showed that the ridge was the perfect balance between three competing factors: the reach of the alpha particles, the fusion power generation rate, and radiative energy losses.
And this whole workflow, from concept to numerical exploration to theoretical explanation, was done in about 6 hours.
6 hours. And here's a money shot. The expert estimated this entire process would have typically taken 6 person-months with 2 good postdocs.
6 months compressed into 6 hours.
A compression factor of about 1,000. That number, $1,000 time, is probably the single most important metric in this entire report. It just fundamentally changes the cost of discovery.
That acceleration factor is the hook. But now let's focus on the novelty. The report claims GPT-5 helped finalize genuinely new scientific breakthroughs. Let's start with that long-standing ERDAS problem, #848.
This is a classic open problem in combinatorial number theory. It asks for the densest possible set of numbers, where if you take any two numbers from the set, A and B, the expression AB plus 1 is never square-free.
Okay, square-free just means it's not divisible by a perfect square, like 4 or 9 or 25.
Exactly. So you want a set of numbers where AB plus 1 is always divisible by 4 or 9 or 25 and so on. The long-standing conjecture was that the densest such set was all numbers that are 7 modulo 25. It has a density of 125.
And the proof was a real team effort.
A beautiful synthesis. Human work and online discussions provided the starting point. But the key sticking point was proving that this conjectured set was truly maximal, that no denser set could possibly exist.
And what was GPT-5's crucial contribution to the proof?
It provided the key strategic step. The idea of using any single unexpected number, a number that's not in the conjectured set, to strongly constrain all the other numbers in the set.
So it's a proof by contradiction almost.
Essentially, if you assume a slightly denser set exists, you take one of those extra numbers, and the AI showed how that one number forces constraints on everything else that quickly lead to an impossible situation. The human experts then took that core idea and formalized the final proof.
A genuinely open problem settled through this human-AI collaboration.
Yes, and we see a similar thing in a very different area: combinatorial inequalities in trees, a niche but very difficult part of graph theory.
This was about proving an open conjecture involving counts of different subgraphs, paths, stars, and Ys. The problem was proving the second conjectured inequality, 29Y, 42P, 144S Lie-Galler.
Right, but first, the expert asked GPT-5 to reprove the first inequality, which was already known. The human proof for it was notoriously ugly 4 pages of tedious algebra.
And what did the AI come back with?
A completely novel proof. It was based on what the researchers called a miraculous identity. Instead of just grinding through the algebra, GPT-5 found a clever way to rewrite the entire expression as a sum where every single term had to be non-positive.
Oh, that's elegant. If every term is 0 or less, then the whole sum obviously can't be bigger than some constant. It turns a huge calculation into a simple observation.
Precisely. It was much shorter and showed a much deeper structural understanding than the original human proof. And then, building on that new, elegant method, the model successfully proved the remaining open conjecture.
This shows it can operate in these really niche areas where general techniques fail, and it can find these bespoke, almost beautiful solutions.
And we saw that again in computer science, with convex body chasing.
Right, which sounds abstract, but it's related to things like robotics and online optimization.
It is. The problem is you're trying to navigate a maze where the safe area, the convex body, keeps shifting or shrinking. You have to stay inside it at all times while minimizing your total travel distance. The challenge is you don't know where it's going to move next.
So the AI's first contribution was just to shoot down a bad idea.
A very intuitive but flawed idea called the follow-the-leader algorithm. GPT-5 was asked to prove or disprove it, and it instantly generated a non-obvious counterexample showing the algorithm could be infinitely bad.
Which saves human researchers a ton of time they would have wasted trying to prove it works.
And then it helped improve the known lower bound for any possible algorithm. A human was working on a proof, but kept getting stuck on a subtle technicality.
The freezing problem.
A freezing problem. And GPT-5 suggested a really elegant engineering trick to fix the proof. Using an epsilon hysteresis switch. It's like a thermostat that doesn't kick in the instant the temperature changes, it waits for a small threshold. This little trick fixed the proof.
So it's not just doing math, it's providing conceptual engineering tricks to fix a human's proof strategy.
And then it generalized the whole result from 2D, which the human was focused on, to any number of dimensions, achieving a new, substantially better lower bound for the entire field.
We've covered these staggering achievements. The 1000x acceleration, solving open math problems. But the listener needs the complete picture. What are the big limitations here? Where did GPT-5 really fall short?
The limitations are substantial, and they're often hidden behind this veneer of high confidence. We saw it with the fusion example. The model can be confidently wrong, it can ardently defend its mistakes, and it can confuse both itself and the user.
It offers up numerical duct tape or just null, noisy results and declares victory.
Which brings us back to the Goldilocks problem. If you, the user, aren't expert enough to know that the physics is wrong or the geometry is flawed, you would just accept the AI's confident nonsense and waste weeks on a dead end.
So it lowers the barrier to computation, but it dramatically raises the bar for validation and conceptual mastery. You have to be an even better expert to use it well.
You do. And this leads to what I think is the most critical concern in the whole report, the attribution crisis, the story of the clique-avoiding codes.
Can you walk us through that? It's a real cautionary tale.
The researchers posed an open problem. GPT-5 initially struggled. It even hallucinated a solution on a form that didn't exist, which is a common failure mode.
The classic proof by hallucinated authority.
Exactly. But then, after some more prompting, it suddenly delivered this elegant and correct algebraic argument for the solution. The human researchers were ecstatic. They thought they'd co-discovered a new result.
But they hadn't.
No. They soon discovered that GPT-5 had reproduced the exact proof that had been published on ArcSIF 3 years earlier by the mathematician Noga Alan. And the critical part is, the model delivered this proof without citing the source at all at first.
That's terrifying. If it can't be trusted to cite a famous mathematician on a public paper, how can a junior researcher ever know if their finding is truly novel?
It highlights this huge risk of deceiving even seasoned researchers. It means the human role in attribution, in verification, in academic honesty is now more essential than it has ever been.
So let's tie this all together. The expert mathematician Timothy Gowers had a great analogy for the LLM's current role.
He compares it to a knowledgeable research supervisor. This supervisor is always available, can solve well-defined subproblems in seconds, can scan the entire world's literature for you.
And can immediately shoot down your bad ideas before you waste months on them.
Exactly. But, and this is the crucial part, this supervisor isn't yet at the level where they would demand co-authorship for a breakthrough idea. The human is still the conceptual architect, the driver, the validator.
And the report emphasizes that scaffolding is key. You have to give it warm-up problems, you have to break things down. You can't just ask open-ended questions and expect magic.
We should also mention the reproducibility challenge. The results can depend on the tiniest details of the prompt, making them really hard to reproduce, which is a big problem for academic rigor.
Okay, let's summarize the big takeaways for the listener. First, the primary value here is acceleration, not delegation. The 1000x factor is the key. It doesn't replace the expert, it makes the expert vastly more productive.
Second, the rise of mechanism-first thinking, in biology especially. The model helps you prune all the bad hypotheses in silico, so you end up doing better, more focused, more reproducible science in the actual lab.
You stop running the 20 failed experiments and run the one the AI predicts will actually work.
And finally, it opens up a whole new design space. It can propose these concrete, testable tweaks to complex protocols, whether it's Kara-POTs or fusion fuel, by iterating computationally before you ever have to do a costly physical experiment.
This has been a really profound deep dive. I mean, it's impossible to look at this report, solving open conjectures, predicting biological mechanisms, doing months of physics in an hour, and not conclude that the pace of science has just permanently shifted.
Absolutely. The report shows what's possible today with expert guidance. And given the relentless rate of AI improvement, it suggests an exhilarating and, yeah, a slightly terrifying time ahead. The job of a researcher is now to master this new collaborative workflow.
So the final provocative thought for you to mull over is based on that 1000x factor. If this level of AI assistance becomes native to lab operating systems, just embedded everywhere, always on, how does the very concept of a hard problem change?
If every expert suddenly operates like a one-person army, now the time barrier to complex calculation and synthesis is just gone.
Yeah.
What new scientific frontiers will become visible for the first time? What questions have we not even dared to ask because we assumed they were impossible for a single human lifetime?
That's the era we're now entering.
It is.
Food for thought indeed. Thank you for joining us for the deep dive. We'll see you next time.